Good evening, everybody. Thank you for joining us for our final British Science Week event. Tonight we have Dr. Mark Parker. He is a former PhD student of the Open University and currently a visiting academic. My name is Katrina Bray. I am one of the communications managers for the Faculty of STEM here at the Open University. Right now, I'm going to hand over to Mark to do his presentation, but I will see you later. So make sure you pop your questions in the chat function on both Facebook and YouTube, and I'll get them over to Mark to answer for you. All right, so without further ado, take it away, Mark.
Hello, so once I load the presentation, we can get going. Right. So yeah, as Katrina said, I'm Dr. Mark A.J. Parker, and I'm going to talk about physics today in this final Science Week presentation. So thank you for coming along. Physics is, it's quite an obscure, it's a broad subject, and it can put a lot of people off just even mentioning physics. So thank you for coming along. I know that chemists and biologists, they feel as if they have the advantage when it comes to presentations because, chemists, they can set off fireworks and mix chemicals. Biologists can show you stuff like drain fluid and bile, which, has shock factor. But I'm hoping to show you that physics has a lot to offer as well. And I'm going to try and do a bit of a whistle-stop tour of the whole subject. So, buckle up and let's get this on the road. So what do I cover today? Right, well, I cover pretty much as much of physics as I can. I use scale as my underlying theme. So we're going to start on the smallest scale with the quantum world, work our way up to the everyday world, then go and look at the astronomical scale for the astronomy type things, and then we'll close with one big question that physics has. So, okay, let's begin with the quantum world, physics on the smallest scale. Right, so before I start anything, the standard model, I write here it provides a framework which describes all known particles and the four fundamental forces of nature. And I say it is currently the best understanding that we have of matter and physics. All right, so we've just started this presentation and I'm already using a qualitative term. I'm already saying best. What do I mean by that? Right, well, you have to remember that science is not static, science is dynamic. And theories are constantly competing with other theories and building and replacing the previous work that's been done. The standard model, it passes the test of a theory because it makes predictions which can be tested with evidence and experiments, and the evidence matches with the predictions to a remarkably high degree. So that's why I say that the standard model is the best model that's available for us. Okay, so the standard model, it covers all of the particles and the four fundamental forces of nature. So you have the familiar particles of protons, neutrons, and electrons. And I have this little graphic, this little atom thing in the bottom right-hand corner of this slide. Atoms don't actually look like this, as I will explain in a later slide, but this is a good approximation just for an explanation. So in the middle, we've got in red, that's the nucleus that consists of protons and neutrons. And then outside, it's the electrons that are orbiting this central nucleus. But it turns out that there is an entire zoo of particles. And I think that zoo is a good term for it because when you think of a zoo, you think of lots of different animals behaving in different kinds of ways. You've got things like polar bears that are swimming around in the icy waters. You have fish, you have avian creatures in cages. And the particles are the same. They behave in lots of different ways. So I mentioned here muons, which are known as the heavy electrons, and antiparticles, which they make up the constituency of antimatter. And when antimatter meets matter, it annihilates one another. Okay, so I'll talk a bit about these four fundamental forces. Gravity and electromagnetism, you probably have a bit of awareness of. You probably know about these from your day-to-day lives. Gravity keeps us on the ground. Electromagnetism lets us see and has other applications like X-rays, which I'll talk a bit about later. But for our, quantum bit of this whistle-stop tour, we're going to need the strong nuclear force and the weak nuclear force. So what's the deal with these? We'll start with the strong nuclear force, right? So if you have two magnets and you try and make the poles touch, you know, like you've got two north poles, they repel one another, they push each other apart. And if you try and stick a magnet to a surface that's not magnetic, it will fall off as well. So in the nucleus, you've got protons and neutrons. Neutrons are neutral, hence neutrons, and protons are positively charged. So surely, you know, the protons should repel one another and not stick to the neutrons. And, you know, all of the atoms should just fall to pieces, and I shouldn't be able to be talking with you, and you shouldn't be able to be watching. The strong nuclear force is the fundamental force that prevents this from happening. And it acts on the scale of just the nucleus, and it sticks the protons and the neutrons together so that this doesn't happen. And that's shown on this very small scale here. But what about the weak nuclear force? That's even more obscure, but actually it's slightly more familiar, because the weak nuclear force governs the decay of particles. And for instance, the fusion reaction in the sun, and it's a sunny day here where I am, you know, this is governed by the weak nuclear force. And as a matter of fact, you know, with the fusion, you're familiar with the heat and the light that you get, but it also produces millions of these other particles known as neutrinos, which, you know, you can't feel them, you can't detect them, they just sweep through you at all times, but you don't know they're there. So what's this image that I have here? Well, this thing is known as a cloud chamber. And for instance, if you've ever seen condensation on a window and drawn, you know, you've written something on there, it's the same kind of principle. The cloud chamber makes the invisible visible by creating a condensate that allows these neutrinos and other so-called invisible particles to become visible via their tracks. So this is, if you could see all of these particles sweeping through you and moving around at all times, the world would look something like this, which is very, very different to what we're familiar with. And each of these particles has, you know, reasons for the geometric shapes that it takes based on the processes that are occurring there. But I won't talk any more about those because that's not the main focus of the talk. So we've got our weak and strong nuclear forces, we've got our protons, neutrons, electrons, and the whole zoo of particles. So now we're in a position to discuss quantum mechanics briefly. So what do I say? I say that quantum mechanics is the study of physics on the smallest scale, and it's concerned with how matter interacts and behaves on this small scale. And it's important to now introduce a concept known as indeterminism before I can go further. Now, to talk about indeterminism, it's easier to talk about the counter version, the determinism, which we're all familiar with. So in a deterministic scheme, it's possible to predict what will happen next when you have all of the information beforehand. You're very familiar with this, you know, in your day-to-day lives. For instance, if you're driving a car, you put your foot down on the gas, you expect that you'll go faster. You put your foot on the brake, you'll expect you'll go slower because you have the information and you know what's going to happen next. Right, in the quantum world, it's different. It doesn't follow this deterministic scheme. So you can't predict what will happen next with 100% accuracy, even if you have the information from beforehand. And this is weird. And I will give some examples of why it's weird in the next slide. So first, we've got the familiar Heisenberg's uncertainty principle, that we cannot know both the position and the velocity of a particle at the same time with complete certainty. So imagine that you're walking, but you don't know where you're going. That's kind of weird, isn't it? And that's exactly the thing that underpins the well-known Schrodinger's cat idea, that the cat's in the box and it's dead and alive simultaneously, and not dead and not alive simultaneously until you open the box and you see what's happened. So with this kind of scheme, there is only after, there is no before. You have to observe to see what's happening. You cannot predict from what happened before because the state's unknown. The second one I mentioned is Pauli's exclusion principle, where two identical electrons cannot occupy the same quantum state. This has a consequence for astronomy, which I'll discuss later. It underpins how you can have something known as a white dwarf star, and I'll talk about that later. So in the bottom right-hand corner, I've just given a photograph of the hydrogen atom, which I think is really cool. This is very small scale, you can see it. In the middle, you got the nucleus, and then you've got the electron cloud around it because you can't see the electron until you've observed it. So it's not the orbiting thing, it's more of a cloud, and that's small scale. And it's amazing that we can take a photograph like that. So that is our bit about the quantum scale. And I'm happy to answer any questions you might have about that at the end of the presentation. So now we move on to the everyday world, so physics on the human scale. Okay, so let's start with Newtonian mechanics. This is the familiar Newton's 3 laws of motion. You've got the law of inertia, that an object remains at rest or in a constant state of motion until acted upon by another force. Newton's second law, which is F equals ma, the rate of change of momentum is proportional to the force exerted. And Newton's third law, for every action, there's an equal and opposite reaction. And finally, there's Newton's law of universal gravitation, which is basically that, objects with masses will attract one another. And, this goes back to gravity 1. Gravity is going to be a bit of a theme of this presentation too. I say the apple drops. It's the familiar formulation that, as Newton's quote was, it was, the discovery of gravity was occasioned by the fall of an apple. And I think when it comes to talking about scientific discoveries, you've got to put into context, when these discoveries were made and how groundbreaking they were. Before Newton figured that out, nobody had any clue about, what gravity was or why we didn't just float up into space. It was just assumed a priori. So he made a lot of, groundbreaking, really, really great discoveries. And, it's difficult to put into context because nowadays we have smartphones where we can Google any information that we want at at our fingertips at the click of a button. So it was a very different time. Okay, so I'll talk about the 3 states of matter, and these are quite familiar as well, I would imagine. And I've chosen familiar images for this reason. So obviously solids, liquids, gases. In the solid, we've got the ice cubes. The particles are all jammed together. They're stuck in this structure. In the liquid, they're a bit more free to move around. It's a fluid. And in the gas, I didn't actually show steam because it's a really terrible image. I show the condensate instead. And yeah, the particles are free to move around. I mentioned this, of course, the 4th state of matter, which is plasma, which is slightly different from what a gas is. And I will explain plasma in a bit more depth when I come to the slide where I talk about the plasma experiment. So giving a bit of context at the Open University, we do research and we do teaching, and these things go hand in hand. And one of the things that we do is we have remote experiments that students can run at home, because one of our missions is distance learning and providing inclusive teaching. And one of these experiments is the gas cell experiment at the Open University. This isn't my experiment. This is an experiment of my colleague, Dr. Anita Dawes, and she understands it a lot better than I do, but I'll try and give you a rundown in the context for it. So what we have here is 2 gas cylinders labeled A and B. The point of the experiment is to use the equipment to take spectrums of both of these gases and figure out what they are. The catch is that one of the gases is known and it's told to you. So you take the spectrum and you compare it with the information that you're given and you get the expected result. The second gas, you have to figure out what it is by taking a spectrum and then going and doing some reading about it. So you might ask, well, what's the point in all of this? So I have to give some context for the experiment. This is in an astrochemistry laboratory. So astrochemistry is a mix of astronomy and chemistry. And the point of the field of study is astrochemists study gas clouds in outer space and try and figure out what they're made of. So you're not able to go up into space and collect samples from one of these gas clouds. You can take a spectrum of it, but it's not quite the same. So what you do is you take a spectrum of the gas cloud out in space. Then you simulate the conditions in the lab, have a vacuum and put in the materials that you think might be there. Then you compare the findings from your experiments with the spectrum up there and see if there's a match. And that's the point of the unknown gas aspect of this experiment, that you have to try and establish what the gas is. Like, do you have ammonia? Do you have water? Do you have ethanol? Do you have amino acids? Because these all have different consequences for life, which is astrobiology, and that's a different field of study as well. So down in the lab, we don't just do astrochemistry, we do plasma, which I'll talk about a bit in a moment. But some of my colleagues also work on stuff like They deal with energy levels of hydrogen atoms, Rydberg states, which have applications for quantum computing. And some of my other colleagues, they deal with the irradiation of matter and radiation, which can be applied for, optimizing and improving cancer treatments. So there's good stuff going on down there, and there's a lot of good research. Right, so the plasma experiment is something that I know quite a bit about because I've worked in this lab. So what happens, how is a plasma different from a gas? That's where I'll start. Well, the point is, in a gas, as I mentioned, the particles are all flying around. But in a plasma, the particles are flying around, but the electrons have been stripped from the atoms to separate the protons and the electrons. What does this mean? It means you've got a free-flowing sort of soup of protons and electrons, which can now conduct electricity because it's got an electrical, it's not neutral. So what happens in this rig? Well, what we have is we've got these two capacitors, and what you do is you put a current over both of them, which induces a potential difference or voltage in between the gap. You then pump a gas through it, which strips off the electrons and turns it to a plasma, because there's now an electrical current, and then the current flows through this gas, this plasma, and it gives this purple color. And if you've got different gases, you can get different colors. And yeah, plasma is different from gas because it conducts electricity, and that's a very different kettle of fish. So yes, next thing I'll do is talk about the electromagnetic spectrum. Before I talk about electromagnetism, I'll mention two guys. I'll mention first James Clerk Maxwell, he was a Scotsman who, he came up with the equations that basically proved electromagnetism as a concept, and they're called Maxwell's equations, and that's how we have a spectrum and understanding of this today. He was a very clever guy. And the second guy is Michael Faraday, who discovered electricity. And there was an anecdote that Albert Einstein, he kept pictures in his study. There was three guys he had pictures of. It was Isaac Newton, James Clerk Maxwell, and Michael Faraday, because he viewed them as the three guys who were like the cornerstone of physics for his time. So yeah, there's a lot of history as well on how this stuff develops. So going back to the electromagnetic spectrum, we have in this visual, the familiar stuff. We probably know about radio waves because we call it a radio because it uses radio waves to transmit. Ditto with a microwave, it's the eponymous microwaves that cook food, but they can also be used for your, TV remote and to, transmit signals. Infrared, sometimes known as heat radiation. So your radiator has this. If you have night vision goggles, really they're heat vision goggles because they can see heat. Then we have visible light, which, allows us to see, so it's very familiar. Ultraviolet, which gives us, tans, and can also be used in fluorescent tubes. X-rays, a medical application for viewing bones that may or may not be broken. And the same with gamma rays, you could use it in medicine for chemotherapy to go after cancer cells. So you could have a whole presentation that talks about the electromagnetic spectrum. It's a very broad thing. But what we're going to do today is focus on the X-ray aspect in this bit of the talk, because there is actually an experiment at the Open University that you can run from home remotely that makes use of X-rays. And it's a Compton scattering experiment. And we actually have a video of it, which I will show and talk you through. So this is the setup, on the left, it's the Compton rig, but on the left here, you've got the X-ray tube. The point of the X-ray tube is when it's switched on, it creates X-rays, well, obviously. But what's the point in creating these X-rays? Well, what you do is you can take these X-rays and you can make a beam with them. That's what an electron gun is. That's the concept of the electron gun. So the beam of X-rays goes through this to the right, through this gap, and then in a straight line, you fire the electrons that come from the X-ray tube. And what's the point of doing this? Well, you aim for the target in the middle, this glass crystal-looking thing. It's a crystal. And the point is that once the stream of electrons meets with this sample, interacts with it, they will scatter out in different directions. And depending on the angle that you set your detector and your sample, you'll get different readouts for the scattering is happening. This is the Compton scattering effect. So the detector is up here on the right, this big silver thing. And, in a moment, we will see how the interface, comes together so that you can run this remotely. Yeah, here it is. So you can look at your settings. You can see what you can do. You can change the voltage. You can change the current. You can change the time of exposure. And you can change the angle of both the detector and of the target. And again, you can run this from home. You don't have to be in the lab to do this. It's rigged up so that you can. So here, for instance, you can knock it down all the way to the neutral position at 0. And then set that up. See, it moves. And then in this configuration, it will go in a straight, the electron beam will go in a straight line. So you should get some, a lot of counts on this configuration. But you can set it to all kinds of other angles. So the second angle it will be set to is not the neutral one. It's going to be 30 degrees, I believe. Yeah, 30 degrees it's set to. So hit that, it will move again. And this time you'll get a different kind of scatter. You'll get a different kind of reading. So the only thing that's left to do in the demo is to actually switch on the experiment and get a reading. So we'll do that now. Start scan. As you can see on the left-hand side, it switches on, and there it is. The X-ray tube comes on remotely. You can't see the electrons traveling through here, but they are, and they're getting deflected. And you can see the spectrum come out on the other end, which is on this chart readout. And it slowly builds up. I think it skips forward, yeah. And then you get these peaks. You're looking for these peaks because it's an abnormal behavior, and it corresponds to what you would expect from Compton scattering. So there's a big one. There's a twin peak, and then there's some smaller ones as well. And I believe that that's the video finished. Yeah. So now we can move on to the astronomical scale. So that's physics on the largest scale. And again, like physics in the lab, we also have some remote facilities at the OU for doing astronomy. So obviously astronomy is the science of observing the universe. This includes galaxies, stars, and planets. There's also black holes and other stuff, which I'll touch on a bit later. And at the OU, we've got the Arrow telescope and the Pirate telescope. The Arrow telescope is here on the bottom left in the dark. This is a radio telescope, so you can have it here or you can have it there in Milton Keynes, and you can run it in daytime, whatever time of day, because you don't have to worry about cloud cover because radio waves go through cloud and you're looking for radio signals. In the middle is the Pirate telescope, which is it's a visible light telescope. Since it's optical, you need good conditions for it. Ergo, we don't have it here or there in Milton Keynes. We have it out in Tenerife instead, where there's a lot of clear skies to get good observations. And the bottom right-hand picture shows that clear sky and why this location was picked for this rig. So I'll start with this Arrow telescope demo. So there it is, the telescope in the daytime on the Milton Keynes campus. And this bit of the video just shows the telescope slewing. And this has been sped up a lot because you couldn't slew it this quickly, it would damage it. So it's just going to spin around. You pick your target, and we'll have a look at the interface in a moment, which is similar to the Compton one that you can run from home. So yeah, once it's done slewing. Yeah, here it is. So it's similar to the one that was previously shown, but this time it's got an astronomical context. So you can see the Skymap here in the middle. You can see for the readout, you can see the interface. And then on the top left, you see the webcam, which shows a live feed of the telescope on the campus. And you can see that there it's nighttime. I mean, you can see the cars driving past at peak times here, but that's not the main function of the webcam. The function is to check to see if there's any damage done to the telescope and if any maintenance needs to be done. So with the Skymap, you pick your target where you're going to aim for, but you should pick in advance, to know what you're looking for beforehand. So in this In this case, we're looking for radio wave signals that are emitted by hydrogen atoms when their electrons go from one energy level to a lower energy level, the hydrogen line. So again, once the experiment is run, we'll be looking for a peak that corresponds to this hydrogen line. So here's the same kind of interface, quick scan, let's see what we find. It fills in slowly, but I think it speeds up in a moment just to show it. We're looking for a peak, remember, peak for the hydrogen line. Just gonna fill up. There it is. So there's the peak. There's slightly a double peak as well, but that corresponds to what we were looking for. And when you take spectra or anything like that, you're looking for peaks in abnormal behavior because that corresponds to some behavior that's happening in the physical system. So next one is the Pirate telescope, which is in Tenerife. So the interface is a bit more complicated, but it's the same kind of idea. On the right-hand side, you've got the telescope, which is a video feed to Tenerife showing the telescope inside. Serves the same function as the one for Arrow to see if there's anything going wrong with the telescope, see if any maintenance needs to be done. And you also have an external camera that sees what's happening from the outside view. So with this one, it's an optical light telescope. So you pick your targets like you do previously, but you sometimes want to have different filters to emphasize different features of your observation, depending on what object it is that you're observing. So again, you can run it from home. It's fully automated once you give it the commands, and it's quite straightforward to do. So once you take images, you can download them and put them on the online repository so that you can call them when you're ready to do, additional analysis on them or to make the images sharper, remaster them, this kind of thing. But all the data can be stored on this repository, and it's quite straightforward. So then, once you've cleared your queue as they've done, you can go down and check what you've saved, and there's a whole list of observations that have been done, who did them and at what time, so that there's a date and time stamp so you don't lose your observations. And then once you've downloaded them, you can, as I said, you can apply other filters and you can remaster them to get what you're looking for. So what are the images that we can get from this telescope? Well, there's some pretty nice ones actually. So I'll take the opportunity to talk a bit about, the cosmos and things we find up there. We have here a star, a galaxy from the side, a nebula, another star, another galaxy, some bigger stars, and another galaxy. So stars have life cycles just like people. You start with this nebula type thing. Once the gas in the nebula compresses down, it gets hot enough for nuclear fusion to start happening. So hydrogen is turned into helium. And once you have enough fusion going on, you're strong enough, you have enough force to balance out the collapse of gravity to push back out in equilibrium. And that's how a star is formed. And depending on the size of the star that you have, its life will end in different ways. So for a star like the sun, it's a smaller kind of star. What will happen to it is it will blow up its outer layers, and then it will retain a core, which will be very dense, and it will be something called a white dwarf. Remember the Pauli exclusion principle I talked about before, right? So what happens in this scenario is the atoms are pushed close together, but there is still, the gravity is not strong enough to overcome something known as the electron degeneracy pressure, which is an application of the Pauli exclusion principle. It means that the electrons can't be forced any closer together because they can't occupy the same energy levels. For a bigger star, you wind up with, the electron degeneracy pressure being overwhelmed, crushing down the atoms so that it only is neutrons. The electrons and protons are forced together, becoming neutral. And you get something known as a neutron star, which is very dense and pulls things in. But it still doesn't collapse further because of something known as neutron degeneracy pressure. You can't force the neutrons closer together. With even bigger stars, even the neutron degeneracy pressure fails, and you get, black holes, which punch their holes in space-time itself. They form wells that not even light can escape from, hence, black hole. So this is on the top right. That's sort of what happens with a big supernova. As I mentioned, that the matter in a big star, the matter collapses down, and then it rebounds off the core, causing a huge explosion. Depending on how big the core is, it becomes a neutron star or a black hole. But you can't see a black hole because light can't escape from it. But similar to the invisible universe, you can imply that it's there. And there is thought to be a black hole at the center of every galaxy, a supermassive black hole, including our own. And you can imply its existence from the existence of an accretion disk in the middle of the galaxy that is hauling matter in and heating it to ridiculously high temperatures so that it emits X-rays and gamma rays. But you can also see it even on the visible. You can see in the middle clearly that something's going on in these galaxies. And these are great images, like all of them. They show, the vastness of the universe. And I've got one more image towards the end of this part that sort of summarizes that. So, okay, we're still on the largest scale. We're going to talk about general relativity, which is Einstein's famous theory. So what does general relativity do? It combines the 3 spatial dimensions with the 4th time dimension to form a geometry of 4-dimensional spacetime. Now, Einstein's genius was to reinterpret gravity as the curvature of spacetime. That's crazy, like no one else could ever have conceived this. That's what a genius is. So the basics of general relativity, as physicist John Wheeler greatly simplifies it, is spacetime tells matter how to move and matter tells spacetime how to curve. So it's a bit like a chess game where both sides, they take actions and the other one has to react to it. It's they rely upon one another. So general relativity provides a very good description, the best description of the large scale universe. And it makes predictions like black holes, but you can actually take it to the extreme and you can use it to study the fate of the universe overall. And this is known as cosmology. That's the study of the fate of the universe. And that's achieved by solving the Einstein field equations for different scenarios, then comparing these to observational data. So what do we have? What's in store for us? Well, this is the universe. This is all of the lots of galaxies, not all of them. An image taken by the Hubble Deep Field. And what's going to happen according to our best current models is eventually, the universe is expanding, it's getting bigger. Eventually what will happen is all of the stars in these galaxies will run out of fuel, and then we'll wind up with a universe heat death. So it's, it'll go dark and cold. It's quite miserable, but that's apparently what is in store for us. But in the meantime, we can enjoy this image, which shows the vastness of the universe, because each of these dots, each of these formations is a galaxy in itself, a galaxy containing, billions of stars like our own. So it's vast. And one of the striking things is it's homogeneous as well. Like in every direction, it's the same. There's loads of galaxies, and yeah, it's a mind-blowing image. It's like the small scale hydrogen one. It's a real eye-opener. Okay, so we've completed our tour. We've gone from the smallest to the largest. So that all that's left for us is to ask one big question. Now, let's bring these ideas together. Okay, so what do we know? Quantum mechanics provides a theory which describes the physics of matter on the smallest scale. Great. General relativity provides a theory which describes the physics of matter on the largest scale. Fantastic. That's great. And in our current universe, we don't have to worry about combining these two because the small scale is the small scale and the large scale is out there. But what about in the early universe when, everything that is and ever will be was contained in a very small quantum size, mass, ball, whatever. And in this case, quantum mechanics does meet general relativity. That is, quantum mechanics needs to meet gravity. But here's the catch. As it stands, there is no theory that can successfully combine, quantum mechanics and gravity. You just wind up in all kinds of trouble. You wind up, throwing errors, as it were. It's like trying to divide by 0. It doesn't work. So a theory of quantum gravity eludes physicists. There are some attempts, theoretical ones, that they're exotic and they make use of additional dimensions. But remember what I said at the beginning of the talk. A theory needs predictions that can be tested. And these conditions, early universe, they're not really things we can simulate. Not like astrochemistry. We can simulate that kind of environment, but not this kind of environment. So until it makes some testable predictions, which would resolve some of the queries that we have with current cosmological models, a theory of quantum gravity still eludes physicists. And this remains one of the biggest open questions in the field. Hey, if you have some ideas, if you think you could be the one to solve it, then by all means, try. But, it's a very, very big question. So I will end this presentation by just showing the two images side by side. We've got on the left, the hydrogen atom, the smallest scale, the smallest atom, the atomic number, the number numero uno, and on the right, you've got all the galaxies in the deep field. So these are the references for the images that I used, and the acknowledgements. We've got Katrina Bray and Louise Hargel. They organized the whole event, including editing, social media, communications, and promotion. Wouldn't have been possible without them, so big thank you to them. Helen Lockett, James Smith, Brian Richardson, Ed Brown, Cross, Peter Sykes from the Open, and everyone else at the Open STEM laboratories, who make sure that those remote experiments can run. Kate Bradshaw provided the video footage. Nicholas Braithwaite was the man behind the plasma experiment. I mentioned Anita Dawes, she did the gas cell. Alan Kalis for the X-ray Compton, and Ulrich Kolb for all of those, the astronomy stuff, those remote telescopes. And finally, a massive thank you for Thomas Webley, Lily Hills, and Josh Oakley, who are lab techs at the OU. They do great work. They support the research, and a lot of this just wouldn't be possible without them. So without further ado, I'll close by leaving this image on the screen, and I'll take any questions that you might have. Katrina, I can't hear you.
Can you hear me now?
Yeah, I can hear you now. Yeah, great.
Oh, my apologies for that. Sometimes headphones, the microphone doesn't always catch on.
Right.
Anyway, I thought the perfect kickoff question, and this is from Chris. She is an environmental science student, but she's actually switching to physics. So she just wants to know, what was your area of study and what made you choose it?
Okay, so actually, I mean, if I can go back to sharing my thing quickly, just to bring back
Of course.
Hopefully it doesn't cause any technological problems. But let me resume the slideshow. Yeah, so I was going to mention this, but I didn't know what my time was like because I didn't have it on the bottom right-hand corner. So sort of, if you talk to, I'm not an astronomer, I'm a mathematical physicist, but if you talk to any astronomer about, their career, trajectory, usually there'll be some anecdotal story where like, oh, my aunt or uncle or parents, they took me out to the countryside with a telescope and I looked up into the sky and I was like, wow, I've got to study that. Like, I want to understand that. For me, it was slightly different. It was this Hubble deep field image really spoke to me when I was a small child. I saw this and I read about the universe, and it's like, the vastness of space was just really immense for me. And I was like, I have to understand it. I have to know. So I learned that the best way to try and understand the universe was through mathematics. So my undergraduate was actually a math degree with the OU as well. And when I went on to do my research, I'd already studied quantum mechanics and general relativity. I had a good grounding. My research was in physics education, and I was passionate about trying to teach physics to other people. So that's sort of how I wound up on my trajectory. And today is a good culmination of that because I got to talk a bit about quantum mechanics. I got to talk about general relativity, and I'm getting to answer some questions from you. So yeah, just follow your gut, and if there's something that really inspires you, go for it. That's the advice I can give.
So, Mark, could you tell us, how did the Hubble Space Telescope manage to capture such a detailed image of the faraway galaxies?
Yeah, so again, I was going to mention a bit of this, but didn't know the time. Right, what happened with Hubble? So obviously Hubble's out in space. I mentioned before that for an optical light telescope, you need to minimize light pollution. That's why the Pirate telescope's in Tenerife. So what Hubble did was it pointed the telescope at a piece of sky that appeared to be completely black, like completely devoid of anything. And obviously, and then it left itself pointing at that for a while, just to gather any, the photons, the light from the faraway universe, if any. And they were astounded when they found that the space that was supposed to be on first observation looked empty, turned out to be full of galaxies like this. So what they did was they found another, hence deep field. They found another section, like here somewhere, like maybe here, in between those galaxies. And they did the same thing, right, let's collect some light from here and see if there was anything else. And that's basically how and they found again, that thing I said with homogeneous, that it was the same. So yeah, to get these images, they focused the telescope on apparently, black space for a long period of time. And then, it turned out that actually there was loads of galaxies, and space was way more vast than anybody could have anticipated.
Brilliant. You've definitely got some fans.
Really?
Right now. And they've asked, do you have a Facebook, Instagram, or Twitter account they can follow to learn more?
Now, this is interesting because I was previously, especially pre-COVID, I was very old school. Like I didn't want to, which is ironic. I work in physics education. We worked in like innovative physics teaching, but I've avoided getting involved in that kind of stuff. But now after doing this talk, I think I might sign up for these things and communicate with people, because it's a great way to reach out to people. It's the first time I've done an online event like this. Previously, as I said, pre-COVID, everything was face to face, but there's advantages to doing it like this because you can reach out directly like that. Whereas if you're in an audience, you might not be able to connect with me. So yeah, look out for me. I might join these platforms, and I'll let you all know.
Absolutely. Just send me your new Twitter or Instagram handle. We'll make sure your fans get that.
Yeah.
Right. So, do you have any advice for current STEM students at the OU?
Just general kind of advice. I mean, I gave a lot of advice to Chris just there as well. So that applies to anybody, follow your gut. But sort of, I guess if everybody's got a different situation, but where possible, try and read ahead. Make sure that you stay, you plan in advance when you want to tackle TMAs and things like that. And if you know that you're not going to have enough time, let your tutor know like well in advance so that you're not going to have time, and ask for an extension. But aside from that, sort of the usual, I mean, this is stuff that applies to pretty much everybody now in COVID, that make sure that you've got an area that you designate as your workspace, for study, and just stick to that. Don't like bring your TV over and start watching it in this place. Make sure that, it's your place for study. And once you're sitting down there, just, get down to it and make sure that you keep yourself motivated, that it takes a long time. It can take 3 years, it can take 6, it can take 9 to 10 years to finish an OU degree, depending on your circumstances. But just do what you can, and don't feel discouraged if you feel like your progress is slow, because there's a lot going on in everybody's lives, especially now. And you can only do what you can do, and you will reach the end. You got to remember that you'll reach the end, and you'll get your degree, and you'll get to go to the ceremony and all of that stuff. So yeah, keep that in mind. I'm sitting here, I did it. I had the same feelings.
And along the same track, one of your younger fans want to know, what is your favorite part of physics?
Oh, that's a tricky, because when I was a child, it was definitely this general stuff. Like I really liked the idea of understanding the fate of the universe. But I became a mathematician first, and I learned the quantum theory and all of the eigenvectors and all of the matrices that were involved with that. So I think it's a toss-up really between quantum electrodynamics, which is, remember the invisible universe I was talking about with the weak nuclear force. Like, I find that fascinating, the idea that particles are created and destroyed just around us right now. I was really moved by that and the mathematical formulation of it. But then there's the general thing, which goes back to my childhood and connecting everything and the galaxies. So it's a toss-up between those two, quantum electrodynamics, quantum theory. But I mean, electromagnetism with Maxwell, his story really, really touched me as well. So it's, wherever math meets physics, which is like all the places, it's sort of, yeah, it's picking a favorite is, because if you ask me to pick a favorite scientist, it would be the same kind of, oh, there's so many, like, which one should I pick? So electromagnetism, I mean, but I did my PhD in sort of like, we looked at education applied to Newtonian mechanics and general relativity and gravity. So I guess that quantitatively would be gravity, like general Newtonian, but just overall, it's, yeah, wherever I can apply math to physics, I love that.
Well, speaking of math and physics, what sort of things do you do as mathematical physics, and what path did you take?
Right. So the modules that I studied, there was the electromagnetism, there was the quantum world, which I thought was I really enjoyed that course. And there was also it was called, I mean, I've got the codes and everything, but there was a general relativity one. There was a fluid mechanics one as well, but that's applied math. It's slightly different. So with those ones, I did basically the first 2 years. The second year you do, I think it's MST 210 these days. I did it when it was 209. They're always changing the codes, but that module provides you with all of the ground knowledge that you need to advance to the electromagnetism, to the quantum, to the general relativity, because it teaches that stuff, the eigenvectors, the partial differential equations, which is just electromagnetism is full of that, the matrices, and just the idea of mathematical modeling, of applying math to physical scenarios. So I think if you're with the OU and you want to study, the electromagnetism, the quantum mechanics, the general stuff, I would highly recommend doing the 209 or 210 as it is now. Do that beforehand to give you the mathematical grounding, because you need the math to understand the physics.
Wonderful, thank you. So we're going to get into a couple of physics-based questions now. And so in what key way does a plasma differ from a gas?
Right, yeah, so I think I didn't make it quite clear. So that, we classified the solids, liquids, and gases based on the structure. And, the familiarity, we're familiar with it. As I said, like the water, the ice, the liquid water, and the gas. But with the gas and the plasma contrast, the idea of stripping the electrons off the gas and separating it into a soup of protons and electrons, that is a game changer, because suddenly it conducts electricity, and that's not behavior that's typical of a gas. So for instance, gas and liquid are both fluids, but gas and liquid are not the same because they don't behave in the same way. Like liquids don't float around everywhere. the same way, you know, gas and plasma. Gas does not conduct electricity like a plasma does. And as we've seen, you know, in that experiment with the purple ring, you know, that's obviously very different from a gas, which is why it gets dubbed the fourth state of matter.
How does one reconcile the existence of black holes with the conservation of matter?
Because in this instance, I mean, again, I'm going to have to make a few assumptions. So we can't create or destroy matter. I mean, in quantum electrodynamics, you do, but you basically, you borrow the mass, like the mass appears and then it disappears. So yeah, that holds. But in this case, the idea is that if you've got, you know, this black hole, your matter gets sucked into it. The matter isn't completely annihilated. It's just stuck within the event horizon. It's within this well. And to reconcile it, it was, you know, Stephen Hawking, Professor Hawking, another great physicist, he came up with the idea of Hawking radiation, that black holes don't exist eternally and forever. They also will dissipate over time. And the idea is that once the black hole dissipates, you should be able to retrieve the matter that was sucked into the hole, you know, from the well, because it's no longer there. So yeah, Hawking radiation is the one that reconciles that. So yeah, you don't, you know, the idea of the black hole, you know, just annihilating everything is a very sort of like romantic idea. It goes somewhere, but we believe that you could retrieve it, you know, if you wait long enough. But I mean, if somebody, you know, gets sucked into a black hole, you're probably not going to see them again. That's like the bottom line, because this takes a long time.
Rita on YouTube would like to know, what would be the most exciting discovery for you when JWST is in full operation?
Oh, the James Webb Space Telescope, when it's in full operation. Ooh, that's a good question. We spent such a long time, you know, waiting for it to become operational. I mean, I'm trying to think, because as I said, I'm not really so much an astronomer, but I think a lot of the it will push astrochemistry on a lot. I mentioned the idea of that because that links to the astrobiology as well. So I'll give a bit of context. I think that if we can find sort of what we determine as the key building blocks of life, you know, amino acids, water, you know, oxygen within the habitable zone of a star. So like the Earth is within the so-called habitable zone of the sun. I think Mars is as well, but I'm not an expert. But if we could find some actual, you know, case studies of locations that, you know, if we could come up with a printout of these are planet systems that could potentially have life, that would be, you know, that would be a huge, because we think we found biomarkers in a lot of places, but it's still very vague. It's not, because we don't have the precision that JWST will finally bring. So yeah, the astrochemistry and astrobiology implications they'll be huge once it launches, you know, when it finally launches. Because I had colleagues when I arrived at the OU who were awaiting data from the launch who never received it. They finished their PhDs and everything without getting the data from the launch. So yeah, we'll just have to wait and see. But it will, when it launches, it will have big implications. But yeah, until it launches, we'll just have to wait.
Well, I think we've gotten through everybody's questions now. Is there anything else you'd like to say?
No, just thank you very much, and I'll keep the social media handle thing in mind. And if the chance arises, I'll definitely look at doing more talks like this, because it seems to have found a good audience. And you know, thank you for showing up. And well, as I said, with physics, it can put people off immediately before you even talk. They're just like, oh no, not physics. But it seems like, you know, I had the audience that I was looking for. They got the talk they were looking for. So yeah, thank you very much, and I hope that I can do more like this and speak with you again, maybe more detail about some of the other topics. So yeah, we'll see.
Absolutely. We would definitely love to have you back on for another talk. Right. Well, we will say thank you to everyone who's joined us, not just for this presentation, but the other events that we ran throughout the British Science Week event. If you missed any of them and you want to catch up, just have a look on the YouTube link that you're watching this right now, or on the Facebook link. You can check our video section and you'll find them there. Until next time, everybody, thank you very much. Goodbye.